So what we need to do is we need to review derivatives from Calculus 1. So this picture right here should look very familiar to you. And at first, we talk about the slope of the secant line. And that gives us then the slope of the tangent line. So you look at these 2 points on a curve, you connect them. That line is what we call the secant line. And what that will give us, if we find the slope of that line, it'll tell us what the average slope over this interval of the curve would be. And then what we do is we look at this distance delta x. This distance delta x is the distance from this x value in that point to the x value in the second point. And what we want is that delta x to go to 0. Why do we do that? Because what it does is it takes this point and starts moving it down the curve towards this other point, thus making the interval smaller. And so what it does is, if you look at this series of pictures here, is it's going to shrink delta x down to 0. And so you see these 2 points getting closer and closer and closer together. Now the line between them is still a secant line, and it's still giving you the average slope, but it's giving you the average slope over a smaller interval. In which case, the idea here is you're trying to find this slope over this interval, but if that interval becomes infinitesimally small, so those 2 points essentially become 1, that slope that you're finding is no longer the slope of the secant line, but the slope of the tangent line. And that was the crux of what you learned as the definition of a derivative. And so you get this limit here, which is the limit as delta x approaches 0 of the slope of the secant line. This is the slope of the secant line. When we take the limit of it as delta x goes to 0, we then find the slope of the tangent line. So this is what we define as the slope of the tangent line. And this is exactly the derivative definition. Now we don't focus so much on the limit definition, except for when we first learn it, because it is fairly cumbersome and it takes a long time to calculate the derivative of many basic functions. So what we instead do is we start to learn the derivative rules. And those are the things that you should have memorized. In order to make it through Calc 2, you have to have your derivative rules memorized in order to continue to move forward. And that's the same if you're going to go to Calculus 3 and pass that. And so now we need to really look at those derivative rules and review those and make sure that you have those memorized. So some of the most basic derivative rules are your constant rule. The derivative of a constant is 0. Simplest thing you ever learned when it came to derivatives. Even the limit definition made this really easy to find, and that's where all these rules come from. Don't forget, these rules don't just come out of thin air. These rules are all proved by using the limit definition, and hopefully you saw the proof of these rules in Calculus 1. But anyway, so if we have y equals 7, and I want to find the derivative of y with respect to x, you should understand this is Leibniz notation for derivative, dy dx, the derivative of y with respect to x. That derivative would be 0 because this is a constant function. Power rule, probably the one you use most often. It was defined at first if n was a rational number, but after you got through logarithms, you eventually said, okay, this will also work if n is a real number. But anyway, the derivative rule here is saying that x to the n, x to a power, this is called a power function, where that power is, again, it was a rational number at first because of the way you proved it, and then once you got through logarithms, it's a real number. But anyway, it was this n x to the n minus 1. You took the old power, brought it out to the front. The new power was 1 less. So a fairly simple idea here. If I want to take the derivative of f of x, the derivative would be 4x cubed. Very simple. G of x here, I would rewrite this as x to the 2/3 first. So it's a power. And then even if it's a fractional power, again, because the power can be any real number, the derivative would be 2/3 x to the 3/2. You couple those two rules with the constant multiple and the sum and difference rule, and it basically allows you to take the derivative of polynomials. So constant multiple rule said if I have a constant times a function and I want to take the derivative of that, what it allows me to do is to pull the constant out front of the entire thing and then just take the derivative of the function itself. Sum and difference rule says if I have two functions added or subtracted together and I want to take the derivative of that whole thing, what it allowed me to do is take the derivative of the first function, take the derivative of the second function, aside from the addition and subtraction, so basically split it apart, and then add and subtract after you take the derivatives. Again, couple all those four rules that we just talked about, and it allows you to take the derivative of these polynomial functions. at which point these should be very simple for you if you've come out of Calculus 1. So the derivative here would be 3x squared plus 4x minus 5. Very simple derivative here, derivative of polynomials. Then you start to get into a little bit more complex derivative rules, product rule and quotient rule. Probably quotient rule, one of the more difficult ones you learned in Calculus 1. Not so much in applying it, but probably simplifying it was where you made most of your mistakes. And for all these, I mean, if you made mistakes in Calc 1, probably it was in your algebra more than anywhere else. And that was after you took the derivative. You had to simplify your answer, and you probably saw yourself making mistakes there. But anyway, product rule. You have two functions multiplied together. You want to take the derivative of that product. What it said is we're not going to take the derivative of both of these and then just multiply the two derivatives together, right? The idea is you're going to take the derivative of one at a time. So I'll take the derivative of f of x, but multiply that by the original g of x, plus take the derivative of g of x and multiply by the original f of x. Now the order in which you do this doesn't really matter because they're added together. Simple way to remember this is usually in prime notation. F times g prime would be f prime g plus g prime f. But the order, again, doesn't matter. I could take this whole thing and I could put it first. I could take this whole thing and put it second. Because they're added, order doesn't really matter. Quotient rule is where the order really starts to matter because there's subtraction involved. So again, we take the derivative of a quotient, numerator, denominator, f and g. We're going to take the derivative one at a time in a pattern here where we're going to take the derivative of the numerator times the original denominator minus the derivative of the denominator times the original numerator, and then have to put that whole thing all over the original numerator squared. Now this is quite a process here. I like to keep the pattern fairly similar to the product rule pattern where it's first and second. I think first, second. Same thing here, first, second. And it's derivative of first times the second minus derivative of the second times the first. If you think of numerator and denominator, first and second, all over the denominator squared. People have silly songs they sing to remember this. Whatever you got to do, you should have the product rule and quotient rule memorized. Here's a fairly basic quotient rule problem right here. If we were to look at this numerator and denominator, those derivatives individually are super easy to do. So if we want to take the derivative, we just have to piece it together properly. So the derivative of the numerator is 3 times the denominator x squared minus 5 minus the derivative of the denominator is 2x times the numerator, which is 3x plus 2. Put it all over the denominator squared, x squared minus 5 squared, and you have your derivative. Now, that's not the way you would write your answer. We would then want to simplify this, so we distribute this out here and here, collect like terms. And so what we end up with here is there's a 3x squared. This will give me 6x squared minus, because this negative has to go in. So what do we end up with? Negative 3x squared. Then we're going to have a minus 4x. And this one here will give me a minus 15 all over x squared minus 5 squared. If you could simplify, you do. There's really not much to simplify here. The numerator can't be factored. And no sense in multiplying this out. So there would be your derivative using the quotient rule. Again, quotient rule is probably one of the more complicated ones, mainly just because from a simplification standpoint, applying the rule, if you remember it, really wasn't that difficult. Then you have all your trigonometric functions, sine and cosine, probably the ones you memorized the best. Derivative of sine is cosine, derivative of cosine is negative sine. You just have to remember the negative here on the sine. Those are pretty easy. I think these four here, or the other four trigonometric functions, are the ones that people need to practice more to memorize them. And really, I can't say this enough, you have to have this stuff memorized. If you have to constantly look it up, it's going to be difficult getting through Calculus 2. So derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant x times tan x, and derivative of cosecant is negative cosecant x cotangent x. And you should have seen why all these derivatives were what they were. Some basic proofs, some by the limit definition, some by just simply using the other derivative rules that we already have, like quotient rule and product rule. So then we could apply them to some of these functions here. So let's look at this first one and look at what y prime equals. Since these are subtracted, we could do the sum and difference rule. Derivative of x is 1. The derivative of tan is secant squared. And that was a very simple derivative. Here we would need the product rule because it's x times secant x. It's a product of two functions of x. So if I want to find the derivative of y with respect to x, I would use the product rule. So 1 is the derivative of x times secant x plus x times the derivative of secant x, again, is secant x times tan x. Aside from maybe factoring out a secant here, there's really not much you can simplify, and factoring out something is not really simplifying. Simplifying to me would be canceling anything out of this. We can't really do that. So this is essentially the answer. I mean, you could rewrite it as secant x times 1 plus x tan x. Again, that doesn't necessarily simplify, it's just another way of writing it. All right, and finally we have this y right here for c. And so that would be that the derivative would be, again, sum and difference rule because of the subtraction here. Derivative of cosecant and cotangent can be done separately. The derivative of cosecant would be negative cosecant x cotan x minus the derivative of cotangent x would be negative cosecant squared, so that would turn this into a plus cosecant squared x. Again, not much you can do here other than if you wanted to factor out a cosecant, but that's not really going to simplify it at all. It was just rewrite it a different way, so we'll leave it at that. And so, again, you should know your derivatives of your trigonometric functions, all 6 of them. These are the ones I see everyone always has down. These are the ones that you need to take the time to practice and review over and over and over again, mainly because of the amount of times you see them. You see these 2 way more often than you see these 4. And then came the big one, the chain rule. This was the most important one of all because it really opened up the amount of functions that you could take the derivative of. So the chain rule is all about composition functions. So you look at a function that looks like this, which is a composition function. You would have learned all the way back in pre-calc, where you have a function inside of a function. And the idea here is we split it apart, right? We say, let's let y equal a function of u, and u be a function of x. Okay? And if you look at these 2 things separately, I could say, let's take the derivative of this thing here, the derivative of y, with respect to u, which is the variable that it's in terms of. And then here I could take the derivative of u with respect to its variable, in this case, x. Really, it's all this one giant function because g of x is inside f of u. But if we split it apart, what the chain rule said to do is to take the derivative of y with respect to u times the derivative of u with respect to x. Now, you didn't really look at it that way when you applied it. What you did apply it is more this notation. This is sort of the explanation of how we get to here, but largely this is what you looked at. And you said, okay, if I have this composition function, I have an outside function and I have an inside function. And what I should do is take the derivative of the outside function, leave the inside function unchanged, then multiply by the derivative of the inside function. That's exactly what this is telling me to do, but it's telling me to do it by first splitting it apart. And again, we don't really necessarily do that. So chain rule, this is really the one that you applied, this version of it. And so this is the typical example you would have seen, where you have some function raised to a power, the power being the outside, this function in here being the inside. So if I want to find the derivative, I do the derivative of the outside first, which would be the power rule. Okay, so 3 comes out, the new power is 2. The inside stays the same, and then I multiply by the derivative of the inside, which in this case would be 2x. If I want to simplify this, I would just multiply these 2 together, so 6x times x squared plus 5 squared, and there's your derivative. This is also a chain rule problem. If you rewrite this as y equals sine x squared, you got to remember notation from trigonometry. This square means the whole thing is squared. That's different than if I wrote this sine x squared, in which case this is being squared only, not the sine. So you got to remember your notation from trigonometry. So anyway, when I write like this problem looks a lot like this problem back here. So if I was to take the derivative, again, outside would be power rule, inside stays the same. Then I multiply by the derivative of the inside, which is cosine x, and there's not really much to do here, so you get 2 sine x cosine x. Then in Calc 1, you kind of took a break from derivatives after you looked at some applications and you went into integrals. Then after you went from integrals, then you took another turn back to derivatives when you started talking about what we call the transcendental functions. And those transcendental functions start off by talking about logarithms and exponential functions, mainly in the form of natural logarithms and natural exponential functions. And so if we look at the derivative of the natural log, you learned that it was 1 over x. Now, you're only going to see this so often. Most of the natural logs you're going to see are not going to be just the natural log of x, but the natural log of some big function of x. So it's probably more beneficial to you to remember the chain rule version of this logarithm derivative, which is the logarithm of u, where u is a function of x, in which case you learned that I should do chain rule, which is the derivative of the outside, which is the logarithm part, which would be 1 over u in this case, times the derivative of the inside, which would be the derivative of u with respect to x. And the quicker way to remember this was just u prime over u. So if you remember, u prime over u is the rule for derivatives, then that'll help us find the derivative of a logarithm. Now, we can simplify taking the derivative of a logarithm lots of times by applying our log rules first. So if we look at this one here, if I decompose this logarithm and split it apart using my log rules, I could write this as log x plus 3 times the log of 2, sorry, this happens sometimes, 2 minus x squared minus 1/2 times the log of 5x to the 4th minus 3. Now, how did I get to that point? Well, these are multiplied together, so they're added. This power here comes out to the front of this logarithm because this was what was raised to that power. This is being divided, so we turn it into subtraction. And again, the power here is 1/2, so the power comes out to the front for this logarithm. Now, this is not the derivative. This is the same f of x, right? But by rewriting like this way, now it's easier for us to take the derivative. So if we go to take the derivative, since these are now added and subtracted together, I can do each one separately. In which case the derivative of log x would be 1 over x plus 3 times, because it's constant multiple rule, the derivative of log of 2 minus x squared. Now if we use this u prime over u, we take the derivative of this, which was minus 2x, over this thing itself, which was 2 minus x squared, minus 1/2, again, constant multiple rule, this logarithm. Well, again, u prime, here's u. This thing right here is u. If we do u prime, we're going to get 20x cubed over 5x to the 4th minus 3. We can do a little bit of simplifying. This 3 can be multiplied in here. This 2 and this 20 can simplify into a 10. And we would come up with 1 over x minus 6x over 2 minus x squared minus 10x cubed over 5x to the 4th minus 3. Other than that, the only other thing you could do to rewrite this, which we wouldn't necessarily simplify it, but would be to write this as a single fraction here. So find a common denominator and go to a single fraction. We're not going to do that in this example because it wouldn't cancel anything. And again, simplifying is canceling. If you just put things together or factoring, whatever, and you don't get to cancel anything, there's no real simplification happening there. All right, then you read exponentials, probably one of the easier derivatives. The derivative of e to the x is e to the x. Again, you don't necessarily see e to the x all the time. You see something more like this, where it's e to the 5x plus 3. And so this is e to a function of x, so e to the u. And so it's basically just chain rule. So it says the derivative should be e to the u times the derivative of u. So the derivative of the outside times the derivative of the inside, ultimately. In which case, if I was to take the derivative of this here, I would get 5 times e to the 5x plus 3. You rewrite the exponential and you multiply it by the derivative of the exponent. Pretty simple derivative rule. But these are the two transcendental functions you learned how to take the derivative of. We will eventually learn a little bit more about transcendental functions when we start talking about inverse trigonometric functions. But that's now where we lead into Calculus 2. So here's your basic set of derivative rules. Again, I think you should have them all memorized. The best way, I think, to memorize these derivative rules and to keep them fresh in your brain is to make note cards for each one. Every once in a while, flip through those note cards. You'll keep them with you as you go through all your classes. Again, depending on how far you go in calculus, calculus 3 differential equations, and you're going to need it in physics and engineering, etc. Keep them memorized, and you will need these to progress through calculus 2.